We're starting section 4.6. This is curve sketching. So the calculus tools that we have developed so far is going to enable us to sketch graphs of functions with high accuracy. Now we used to do this in pre-calculus a lot too, but we weren't able to say where there was a maximum, local minimum, and so on and so forth. So what you want to find is the key features of the graph. And number one, the domain of f. Where is f undefined? Where am I supposed to sketch the graph of f? And then you want to find the symmetry if there is any, if f is odd or even, usually neither of them. Intervals on which f is increasing or decreasing, which you use f prime for. Intervals which f is concave up or down, you use f double prime for that. You want to find local extremum points using first or second derivative. Inflection points, points where concavity changes, and horizontal or vertical asymptotes. So let's do an example of curve sketching. The function is f of x equal to x to the fourth plus 2x to the 3. The first thing that I want to do is to take the derivative of that, and then it ends up to be 4x to the third plus 6x to x squared. And so the next thing that I want to do is to find the critical values for this function. Function exists everywhere, the f prime exists everywhere, so I have to find the zeros of it. Therefore, I have to factor this. I say 2 is a common factor between them, and then I'll go 2x to the 2, and what is left out of the first one is 2x, and what is left of the second term is 3, and you set it equal to 0, and you end up with x equal to 0 is a critical number, and x equal to -3/2 is a critical number. The next thing that I want to do is I want to use these two before taking the second derivative. I'm going to use these two to find the intervals of increasing, decreasing, and one more thing. So this is f prime. I'm putting -3/2 and 0 on the interval. Then I'm going to use this one to find the sign for f prime. That's one that I have already done factoring. I use the old trick. F prime is a cubic polynomial, and with a coefficient positive, leading coefficient positive. Therefore, if you remember, it looks like these are the endpoint behaviors. So I will have a positive over here and a negative over here, because the right end behavior is going to positive infinity, the left end behavior is going to negative infinity. Now, so I will have positive and negative. Then I'm going to look at the roots. -3/2 comes from this factor. This factor is of order 1. That is an even order. Therefore, sign changes when I cross over -3/2. But x equal to 0 is of order 2, which is an even, and the sign does not change. So I already had set that one up correctly. And so positive, and then this gives me the increasing, decreasing for f. Decreasing, increasing, increasing. So the intervals of increasing, f increasing on -3/2 and 0 and 0 and infinity. Notice that I don't put -3/2 and infinity, because at 0 f prime becomes 0. So there is a break right there. It's not strictly increasing in there. And so it's going to be -3/2 and 0 and 0. My 0 is a little funky, and 0 and infinity. And f is decreasing on -infinity and -3/2 on this interval. So that I figured out. Can I tell where is if there is a min or max point? Yes, I can. At -3/2, x equal to -3/2, I see at bottom of the hill there is a local min. And so far so good. The next step to do is to find f double prime and do the same routine with it. So I'm going to use the version of f prime that is not factored, because that's an easier one to take the f double prime on. F double prime of x is 12x squared plus 12x. And that now, what I know to find the intervals of concavity, I have to find the zeros of f double prime, so I can actually find the signs of f double prime. Finding the zeros of f double prime is to find the signs. And so I have to factor 12x. And then this will give me f prime is 0 at x equal to 0 and also at x equal to -1. Now, from here, I can go about and find the intervals for f double prime. Intervals for f double prime will give me like -1 and 0. And f double prime is a quadratic equation, the quadratic polynomial, and the leading coefficient is positive. Therefore, at the 2n behavior, I will have positive. Again, remember the 2n behaviors are going to be like that for the polynomial. And I'm sorry, I can't show my hands, but we usually raise our hands for n behaviors, right? And so now, in here, f double prime at x equal to -1, the order of the roots is even, odd, it's 1, and so the sign changes. At x equal to 0 again, the sign changes. Therefore, I have here concave up, here concave down for f. Now I have a lot of information, and there are a few more pieces of information that I got. I actually here the concavity changes, so the point of inflection at -1, and here concavity changes, so another point of inflection at 0. If I plug in these 3 points in the original, and that's the only time I'm basically using the original in this question, and by just finding y values is the only thing that I do. And so for these points, if I plug it into original, then I have y value, and I can put those points on the graph, and then just go about with each piece of the graph. What I need to do is basically put all the increasing, decreasing, and concavity together in one piece, and then use that to find how each piece looks like. Before doing that, let's mention a few things. First of all, this is a polynomial, so there is no vertical or horizontal asymptote for it at all. So you don't have to worry, don't worry about asymptotes. It is not an odd or even function, so don't worry about symmetry either. So that's the two things that you want to have in mind. Now let's put everything together. So if I put everything together, so we want to put everything together. How do we do that? Putting all the concavities and increasing, decreasing together. What are the points that I have? I have the lowest that I have is -3/2, and then I have -1, and then I have 0. Anything before -3/2 is decreasing. That's the tangent line. Between -3/2 and -1, between -3/2 and 0, it's going to be increasing. And then after that also is going to be increasing, right? And then now let's put in the concavity in it. Between everything below -1 is going to be concave up. Therefore, I will have a piece above, another piece above. Then after -1 until 0, we'll have concave down. So I have a piece below. And then between 0 and infinity, it's concave up. So these are the blue lines, the blue curves are the shape of the graph between these points. Now, what you do is you basically put in -3/2 over here, and then -1 over here, and 0's over here. And you, the points that you have, we said inflection points are -1 and 0, and then -3/2 is a local minimum. You plug in -1 into your equation. -1 to the power 4 gives 1, minus plus 2 times -1 to the power 3 is -1. So it's 1 minus 2, which is -1. So you have the point -1 and -1, inflection point, and also a point 0 and 0, another inflection point. Let's put those points on the curve. 0 and 0 is right here, and -1 and -1 is right there. And then you have to plug in -3/2 in the equation, and the answer is going to be it's going to be a rational answer, but the approximation is going to be negative. So -3/2 is -1.5. The approximation of the solution, the y value is -1.7, and so you will have right here a point. And so if I put in the shapes of the curve, I can see before -3/2 I should have this shape. Let's change color. Let's change color like this. And then there's a minimum here, and then I will have this shape between -3/2 and 1, or -1.5 and 1, -1. And then I will have this shape, which is like that, and then I'll change to this shape. So there's a concavity change here, and I want to reflect all of that in my picture. And this is a more accurate picture that we can draw than we did in pre-calculus. So we will do more of these graphing. Now, let's study the graph a little bit more. As you see in this graph, the inflection points are 0 and 0, and -1 and -1, And the local minimum over here is actually a global minimum. And so all that we put together gave us this information. Let's do iClicker question 1. Let f of x be equal to ax plus b over x, where a and b are both positive number. What are the critical numbers of f of x in the domain? So I hope you paused, and now it's time to do the question. So to find the critical numbers, all I need to do is to take the derivative, which a is the constant, x is the variable, a is constant coefficient, so I get a. And then here b is the constant coefficient, so a is a constant coefficient, and b is a constant coefficient times 1 over x. So b stays, it's a coefficient, and then 1 over x becomes negative 1 over x squared. And then what I get is ax squared minus b divided by x squared. Now, when I'm finding the critical numbers, I'm finding both where the derivative doesn't exist and where the function within the domain where the derivative doesn't exist, and where the derivative is equal to 0. Where the derivative doesn't exist is when the denominator is equal to 0, x equal to 0, right? But I look at the denominator over here, and so if x does not exist at x equal to 0, so this is not within the domain, it's not a critical number. Now, the other part is I have to set the numerator equal to 0 to find where the function is equal to 0. And when I set the numerator equal to 0, I get x squared is equal to b over a. That is x is equal to plus minus square root of b over a. And that's the answer, C.